Alrighty, welcome back. Today we're just going to go over the sine, cosine, and area rules for non-right angled triangles. Just going to do a couple of examples so that you can see the thought process of how we would apply these rules. But first, let's just recap these rules quickly. And the nice thing is that they all work off a common triangle. So if we draw a non-right angled triangle, any non-right angled triangle, but I'm just going to draw it like this. Maybe that's a little bit too close to a right angle. Let's draw it like this. Okay, non-right angled triangle. Let's label the sides like this. So we'll say this is C. We'll say this is B, and this is A. Okay, those are the corners or the angles in some sense. And then we would label this side as small c, small a, small b. Okay, so we have three important rules that come off this triangle. Firstly is the sine rule. So from this, we have the sine rule, which tells us that if we take the ratio of the sides to their opposite angles, the ratio is always going to be the same. So it's going to look like this. The nice thing about the sine rule is that it's flippable. When I say flippable, it means that we could have moved all of the tops to the bottoms and vice versa. Okay? But it's really nice because it gives us a ratio to work with. That's the first one. The second one is the cosine rule, which tells us the order of the letters doesn't matter, but the position of them does. So what I mean by that is we can say c squared is equal to a squared plus b squared minus 2ab cos c, where c has to be the opposite angle to the side by itself, right? So these have to be quote unquote paired. Okay, this is the cosine rule. And then the last one is the area rule, which simply tells us that the area of the triangle is equal to half AB cos of C. Sorry, not cos, sine. Sine of C. Okay? In other words, it's equal to two side lengths multiplied together, multiplied by the sine of the angle in between them, and then you just take the half of that. Okay? In case anyone's wondering where this sine comes from, this sine is the height. Okay? It just so happens that we don't have a right angle triangle, we just take the sine instead. Great. Okay, so those are our three rules. Let's do three examples to see how we apply them. So this is example 1. Mr. Lung is standing at the point X and looks up at an angle of 18 degrees to the top of a flagpole. He walks in a straight line forward to Y and finds the angle to the top is now 42 degrees. Cool. We want that there's one piece of information that I forgot. He walked 20 meters. Okay, that's important, and we'll see in a sec why. Then we want to find the shortest distance from Y to the flagpole. Shortest just means straight line, so that's going to be like the side length of a triangle and the height of a flagpole. Okay, so always draw a picture. If you're not drawing a picture for a question like this, it's going to be very, very difficult. So let's draw our picture. We'll label this point here as X. Okay, let's draw in our flagpole. It's kind of like this. Now, we're going to assume that we're working with flat ground. You can obviously clarify with your teacher if you're not convinced. Okay, so we can sort of draw this line here, like this. We can assume this is a right angle. Okay, this is kind of our flagpole. Okay, we're told that he looks up at an angle of 18 degrees to the top of the flagpole. So if we draw this, we know that this angle here is 18 degrees. Okay, Then we're told that he walks in a straight line forward to y and finds the angle to the top is now 42 degrees. So we can label a point, let's say here. We'll label this y. And when he looks up, this angle is now 42 degrees. Obviously not to scale. And we know, importantly, this is why it's important because otherwise we won't be able to apply one of our rules. We know that this side length here is 20 meters, specifically from x to y. Okay? Great. So now we're going to apply, we're going to see what rules we can apply. We want to find the shortest distance from y to the flagpole. Okay? In other words, we want to find the length of the blue dotted line. Okay? We want to find the length x. Okay? Actually, let's not use x because we've already got x. Let's label it a. We want to find the length a. So how are we going to do that? Well, we can't just use our normal trig ratios. We don't have enough information for this right-angled triangle, but we can see we've made a non-right-angled triangle, right? X, Y, and the top of the flagpole. So let's fill in a couple of angles, and then we should be able to apply some of our rules. Firstly, we can know that this angle in here is just 180 minus 42, which is 138. Now, do we have enough yet to find the length? Not yet, but if we label one more angle, we will. We have this. Makes a triangle, right? So we go 180 minus the other two. So 180 minus 146, I believe, is 34. Okay, let me just confirm that just to make sure. 18 plus 138 plus 34. Whoops, I overcalculated. I can't do maths apparently. It should be 24. (24). 18 plus 138 plus 24 equals 180. Perfect. Okay. So now we have enough information because now we can apply the sine rule. Because now we have this and we have this, which gives us a pair, right? It gives us a pair, a side pair, and an angle pair, and we've got another angle to work with. So we can write this, sine rule. We're going to solve for the side length, so we're going to say that A over sine 18 is equal to 20 over sine of 24, okay? Which means that A is equal to 20 times sine of 18 over sine of 24. Let me get a decimal approximation. 20 times sine of 18 divided by sine of 24. It's roughly about 15.19 meters. Okay? That's the value of A. All right. Then we're asked to find the height of the flagpole. In other words, we're asked to find this. Okay, we're asked to find H. Now you could find H using the sine rule again, but you don't have to. You've got a right-angled triangle. It's a right-angled triangle. And we know what the hypotenuse is now, right? So we can say that sine of 42 degrees is equal to H over A. But we know what A is now, right? Because we found it up here. So we can say sine 42 degrees times A is equal to H, which means H is roughly sine 42. Obviously, there's a bit of rounding error, but that's okay. About 10.16. And we're done. We've used the sine rule to work out the first side because we needed to work in a non-right angled triangle. And then we just used the normal sine ratio to find the other one because it was right angled. We're done. Great. Okay, example 2. Mr. Lung is playing ice hockey. He's 2.5 meters from one goalpost and 3.4 meters from the other. The posts are 1.83 meters apart. I've never actually played ice hockey, but I do like ice skating. So anyway, find the angle he must shoot in to score from his position. Okay, so again, let's draw a picture. Let's say that the goalposts are like here. Okay. He's 2.5 meters from one goalpost and 3.4 from the other. So he kind of has to be at a bit of an angle. So I guess let's put him here. And we can say this is the longer one. Doesn't really matter where you put it. You just got to label the side lengths correctly. This is 2.5 meters. We know that the goalposts are 1.83 meters apart. And we want to find the angle he must shoot in to score from his position, which means that there's a certain angle that if he goes over, he's going to not actually score. So in other words, we're asked to find this. We're asked to find that angle, right? So we look at this and we go, can we apply the sine rule? No, we don't have any pairs of sides and angles. But we do have 3 sides. And there is a rule that relates 3 sides to an angle. It's this one, the cosine rule. So we're going to use it. Cosine rule. Half of the battle is actually just identifying what rule you need to use. After that, to be honest, it's just a bit of algebra. So the cosine rule says that if I take the side opposite to the unknown angle, in other words, 1.83, and I square it, it's going to be equal to 3.4 squared plus 2.5 squared minus 2 times the two things again, times the cosine of theta, because they're opposites, right? They're opposites. Okay, so now we just do a bit of simplifying and we solve for the angle. So we go 1.83 squared minus 3.4 squared minus 2.5 squared equals -2 multiplied by these things. Then I'm just going to whack this into my calculator and simplify it. If you don't trust me, do it yourself. 1.83 squared minus 3.4 squared minus 2.5 squared equals -14.4611 is exactly equal to -17. Wow, okay. Great, times cos of theta. Now we just divide. -14.4611 over -17 equals cos theta. Now, you could get a rounded value here, but why bother? We're about to take an inverse cosine. So let's keep it in exact value format as long as possible. Cos inverse of, the two negatives will cancel out, so we don't have to worry about that. Is equal to theta, which means that theta is roughly, make sure that your calculator is on degree mode. You could put it on radians, it doesn't really matter. But most of the time with sine and cosine, we assume we're working with degrees. At least the sine and cosine rule, that is. Roughly about 31.72 degrees. Okay? If that's the angle that he's allowed to look in between, if he doesn't, as in if he starts looking at one and then looks at the other, if he overshoots that, he might miss. So that's our answer. Great. Okay, last one. Example 3. A triangle has an area of 22.4 centimeters. If one of the sides is 10.3 meters and another side is 8.4, find 2 possible angles that could connect these sides to satisfy the area. Okay, so firstly, the interesting thing that we should note is, obviously we've got this word area, so we're going to be using the area formula. Fair enough. We're going to be using the area formula. Just move my mic a little bit. There we go. But the other thing is we're asked to find two possible angles, which is really, really interesting. We'll get to that point in a second, but let's find one of them, I guess, and then we can see how we can find the other one. So again, draw a picture. Triangle, we know it has an area of 22.4 centimeters. One of the side lengths is 10.3 and the other side is 8.4. Find two possible angles that could connect these sides to satisfy the area. So let's draw a triangle like this. Boom. Boom. Okay. We can say that this is 10.3, this is 8.4, okay, and we connect this. We don't actually care what the other side is, but we know that its area is equal to 22.4, right? And we're asked to find this. So we have our area formula that connects two side lengths and the angle in between them up here. So we're going to use it. Area is equal to half AB sine C, right? And then let's just fill in some stuff. So 22.4 is equal to half of 8.4 times 10.3 times sine C. Okay? We're trying to solve for C. In fact, let's replace C with theta. All right, so now we just do a bit of algebra, right? So we multiply by 2, 44.8 equals 8.4 times 10.3 sine theta. And then we're just going to divide off by whatever those brackets are. So 44.8 divided by 8.4, then divided by 10.3. In fact, let's just divide them by the multiple. So I'm going to do it on my calculator, but really we're going 44.8 divided by 8.4 times 10.3 is equal to sine theta. Okay, and in fact, let's not even simplify that. We'll just leave it as a ratio because we're going to take the sine inverse anyway. So sine of -1 of 44.8 10.3, and we'll just chuck this all into our calculator. So theta is roughly, actually I'll move it down because I'll make a point in a second. Theta is roughly second function sine 44.8 divided by 8.4 times 10.3. Be careful to make sure that you're dividing by that multiple thing. Order of operations matters. So theta is roughly about 31.18. Okay, now that's one angle. Makes sense, right? 31.18 makes sense that it's the size of that angle, of this angle in here. 31.18 degrees. Now, the question said to find 2. How on earth would we find 2? Well, we have an interesting thing, and this is where we reference something which, if you're in my class, I mentioned it, but we didn't go over it too much, which is why I'm doing it here. It's called the ambiguous case. Okay? Because there's a very, very important thing that we assumed here. We assumed that the 8.4 was the shorter side on the top, which we didn't have to assume. You actually might have noticed I paused a little bit when I did that because I wanted to make this point now. The ambiguous case comes from the fact that sine is positive in quadrant 1 and 2, right, from our unit circle. Boom. It's positive here and it's positive here, which means there are 2 angles of sine that will actually give us the same value in this bracket. Just let that sink in for a second. There are 2 angles of sine that will give us the same values in this bracket. Remember, sine measures the y coordinate, right? But there's two values, right? It could be here, or it could be here, right? Where these are the same. So how would we find it? Well, firstly, let me let me draw the triangle to show you what this actually means. The ambiguous case says we could have drawn this. Right? With this being the angle. Oh, no, sorry, that's actually very wrong. That's not what I mean to draw. I mean to draw this. Could have drawn this. There we go. That's much better. We could have drawn that, right? Where this angle is now obtuse. It's greater than 90 degrees. But that's okay, because we can just say, in this case, okay, the equations still reduce to this, okay? But we just recognize, but theta is in quadrant 2, right? Therefore, and you can think about this for a sec if you need to, by symmetry, using this idea here, that we could have taken this angle, right? This angle could have been 31.18. Or we could have taken this one, where this angle is 31.18, which means if that small angle is 31.18, what's the whole angle? Well, by symmetry, theta can equal 180 minus 31.18, which is roughly 148.82. 148.82 degrees. Because from here, we could have either taken the sine value, as in the thing that ends up from this equation here, tells us that we could have either been here or we could have been here, right? Which means we need to find both angles that give us that case, which makes sense geometrically because there are two different triangles that we could have drawn to make this happen. Okay? A bit of a tricky question. Interesting. All right, I hope that's helpful to use the sine, cosine, and area rules. Yeah, it's all about identifying which rule you need to use and then finding the relevant information. Cool? Have fun.